In this video, we're going to explore how to answer a data testing question. So basically in the data analysis question, what we're really doing is doing a practical report. So what that will require us to do is maybe look at variables, methodology, safety, data analysis, graphing, determining mathematical relationships, and concluding. And often what happens is you're given an exemplar. Now here's an exemplar that has been set up. Now you're given a load of information such as an electric current passed through a heater element, which is a simple coil of wire attached to a power supply. The element is used to heat a beaker of water for a certain amount of time. The current flowing through the wire was increased and the temperature of the water reached was measured for that specific time. The data for this is shown below. So you may be given a table similar to this where we've got current and we've got temperature rise. Then you're asked a number of questions based on this material. Now the first one we've got is to write a hypothesis. So from this I can conclude that as the current increases, so does the temperature rise. Now you then might be asked some of the knowledge as to why this is coming about. And from this what we would try and put together is say, well, as the current increases, what happens is we get more resistance. More resistance means that the electrons are finding it difficult to get through. We get increased friction. This increased friction as the electrons goes through, which links to the resistivity of the wire, causes an increase in the temperature. Thus, as a result, we get an increase in delta T, or the temperature rise. The next thing is we're going to design and plan a test, a practical to test this hypothesis. So here I've got a very simple circuit which I've put together, and I'll just explain through it. So we've got an ammeter here, we've got a variable resistor, we've got a variable power source, we've got a thermometer, a coil, and some water, and a beaker. And then what we would then be doing is we would then write a workable method. So we might have something saying things like we might need to know something about a rheostat for a variable resistor. We would use values such as I's got to go from 0 to 5, and then I want you to try and think about your control variables. What things do you keep the same, such as same size beaker, the thermometer was put in the same place. Also look at your independent and dependent variables and how you're going to measure those. So you may have things along the lines of the coil of wire was the same length, material, number of coils, got the same voltage, etc., etc. We then have to run through what sort of safety issues will be involved in this practical. So we might have things like water spillage, you might have electricity and water, they don't tend to mix particularly well. You may have heat which is generated, so you've got to be careful there, and knocking over materials. These generally come into a common sense factor, and if you apply them and then say how you deal with them, then it shows that you're understanding how the practical works. You're then asked to basically come up and plot the data, and from this we're going to use our graphing skills. So initially what we're going to do is we're going to plot the data that we've got here. Current is our independence, it goes along the bottom, and temperature is going to be our dependent going up the size. So I'm very quickly going to put together a scale. I'm going to label it and plot all the points. In this case I'm going quite quickly, and we'll notice that some of the points don't fit on particularly well, but we should produce a curve which is generated here. Now the question is, what is the relationship for this? Well, we've got delta T is proportional to I squared. We've got an exponential curve that has been generated. So to process this, what I've then got to do is to square each of my current values. So I take my I squared, my I value, and I'm going to square it. So 0.5 squared, 0.25. 1 obviously is going to come out as 1. And I'm just going to run through each of these values with my calculator and square them. Here we go. And obviously 4 squared is 16. So then the next thing I've got to do is to plot I squared against delta T to produce a straight line graph. From this I can then draw a line of best fit and work out the gradient. So I squared is going to go along the bottom, and then the delta T is going to go along the top. So I'll quickly run through this now. Just deciding where to do it. The scale's not great with this graph paper. Generally you'd be given something in an exam which is easier to work through. I've sort of manipulated this data just to help out. But what we should see here is we're getting a line, yeah, nice straight linear line. So I'm going to take the line of best fit through here. Okay, and you can see most of the data is put on the line, which is good. So does it prove that the hypothesis is correct? Well, the answer is yes, because as I increases, so does delta t. However, from this graph, I've ascertained that it follows an exponential function, so delta t is proportional to I squared. So although it's not entirely correct, I can accept the hypothesis because it was so generic with respect to it's going to increase. Now from this, I've got to derive a mathematical equation. Now I know that basically I get delta t is going to be proportional to I squared. Now that on its own basically does not allow me to draw a graph because so delta t proportional to I doesn't allow me to produce it in the equation, but delta t proportional to I squared does because it's a straight line. With it being a straight line, it means that y equals mx plus c can be applied, where m is going to be the gradient of the line and c is the intercept. Now c goes through 0, 0, so all I have to do is to calculate the gradient of that straight line of delta t over I squared. So it's the rise over the run. So basically I'm going to go back to my graph and see which point fits best on my graph. So I'll just get my ruler. Okay, so let's have a look. Well, this point seems to cross the line quite nicely. I'm going to use a red pen. It's not very clear, but basically what I've got there is 12.5 is my run, and 20 is going to be my rise. So in order to calculate the gradient, I'm going to do my rise, which is 20, over my run, which is 12.5. Now this gives me a value when I put it into my calculator. 20 divided by 12.5 is a gradient of 1.6. Okay, so as a result, y equals 1.6x plus c, but we've got to realize that y is going to be delta t and x is going to be I squared. So what I then get is that delta t will equal 1.6 I squared. So that's my mathematical formula. So from this, I've been told that there's a constant for this relation of 2.5 degrees C per amp squared. So to work out the error, I then do the theoretical value minus the experimental value, divide that by the theoretical, and times by 100, turning it into a percentage. So I know that my theoretical is 2.5. I know that what I've experimentally worked out from my value is 1.6. So if I take those two away, what's left over, the difference between those, is the error, and convert that as a percentage, I end up with 2.5 minus 1.6 equals 0.9. Divide by 2.5 and times by 100 gives me 36%, which means a third of my data is a mistake. So from this, as I say, a third of my data is incorrect. So obviously there's got to be changes, although the line of best fit fits quite nicely, which means I'm precise with my data, but there was something wrong with the practical. So what could I do to actually improve the actual practical? And from this, what we then have to do is to come up with an idea as to what we could do. Well, we could increase the number of current values taken. We could replace the water on a regular basis. So anything which you think is necessary or is worthwhile can be written down here, and you just need to explain it. Well, I hope that makes sense. So thank you for watching, and bye for now.